All right, so last time we looked at the cofinite topology. We have a non-empty set X, and we define our open sets as the empty set union all the subsets of X whose complement is finite. And I think we use the prime notation. I keep forgetting which one we use. So the claim is that this is a topology, and it's called the cofinite topology. So I want to work through the proof with you. We started this last time, but didn't finish it. So first things first, it's clear that the empty set is in F because we defined it that way. Okay, we can also say, furthermore, since X complement is the empty set, which is finite, then X is in our set of open sets. So that's good. We've got the 2 of the 4 already. And so now we want to look at arbitrary unions. That's the key part here. So let's let the union of, I think I'll use y's. So let's say alpha and lambda of y sub alpha. So lambda is my index set. It's arbitrary. It could be finite, as in 1, 2, 3, 4, 5, and I'm done. So this could be a finite list. It could be countably infinite, like the natural. So I could have y1 union y2 union y3 forever. It could even be uncountable. It's truly arbitrary. So I've got this union of open sets. So let's write that. I've got a union be an arbitrary collection, be the union of an arbitrary collection of open sets. So we need to show that this thing, this set here, this union, actually lives in F, that it's actually open, if you want to say it that way. So a couple of cases here, just like before, we've seen this already. We do want to consider the fact that it's possible that all of these sets that we're unioning, they could all be the empty set. I could have the union of a bunch of empty sets here. Oops, I'll write it like this. So on and so forth. And in that case, we're done, right? Because the union of a bunch of empty sets is the empty set. So we can say if, by some chance, this union is the empty set, then this thing is in F, and we are done. So now we're going to assume it's not. Okay, so assume that this arbitrary union of y alphas is not the empty set. Well, that means that there's at least some set in this collection of sets, right? I've got all these y alphas. At least one of them is not empty. So let's assume that this whole union is not empty. And then we can say, then there exists some particular index, we'll call it alpha naught in lambda, such that y alpha naught is not empty, and that's going to be important for us. And now, as you'll see in a lot of these proofs, especially as we get into closed and stuff, we're going to use De Morgan's law here. It really comes in handy. If you don't remember that, look back in your book, look it up. It's there. It applies to arbitrary unions and intersections. And so let's just go ahead and note, what does it mean, right? What does it mean for this set to be in F? It means that the complement of this set needs to be finite. So let's go ahead and do that. So let's instead of saying let's say then this arbitrary union complement, well, by De Morgan, that's equal to the intersection of all of these y alpha complements. And I am really trying to use the prime notation. That's actually what I thought I preferred, but apparently I like the C's. Okay, so when we take the complement of this arbitrary union, then we get this. We get the intersection of all of the complements. Okay, and I want to point out to you that this intersection of all of the complements, it has to be contained in our particular y alpha naught complement, right? Y alpha naught is in there, it's in the list, and the intersection is contained in every one of the sets in this list, so it's contained in there. And now what do we know? We can say, but look, y alpha naught complement is finite, since y alpha naught is open. And so if this set is finite, then this one is finite as well. So thus, this set y alpha naught complement is finite, which, by the way, that's the same as this thing. And so we can say that this arbitrary union of y alpha really is in F as claimed. All right, what's the last thing we need to show? We need to pick two open sets and just show that their intersection is also open. So we can say, finally, choose, I'll call it y1 and y2 in F. These are just arbitrary open sets, and we can say we need to show that y1 intersect y2 is also in F. But let's think about it. y1 intersect y2 complement, it's actually the same trick. That's the same as y1 complement union y2 complement. I'm using De Morgan again the other way. And we know this is finite because y1 is open. And we know this is finite because y2 is open. So we can say which is a finite set since y1 and y2 are open. So now we can conclude and say thus F is a topology on X. I'm going to end this video, and then I've got one or two more. We're going to introduce the idea of a closed set and just prove some really quick short proofs about that, and then you guys are ready for the homework.